In this lecture, we're going to talk about what happens when the most massive stars cause collapse.
Well, at the end of the lives of these supermassive stars, with masses greater than about 25 to 30 times the mass of the Sun, even the neutrons in the collapsing core eventually cannot provide enough pressure to support the neutron star against gravity, so it collapses further. So the question is, what happens next? What happens next is known as a black hole, and to understand that, we're going to need to understand just a little bit about relativity, special and, more importantly, general relativity, which incidentally this year marks the 100th anniversary of Einstein formulating the general theory of relativity. So let's talk about relativity. So special relativity was published in 1905, general relativity in 1915, and is based around a set of principles. Relativity is about formulating a theory of relative motion. What happens when something moves relative to something else? Which sounds like a really basic question. It was Einstein's genius to realize it was anything but a simple question. Now, experimental evidence showed that the speed of light was a constant. So Einstein built that into his basic theory of relativity. Speed of light is a constant and nothing can travel faster than the speed of light. That is about 300,000 kilometers per second. And that one fact brings about far-reaching consequences. For example, consider this train robbery. A train is moving at 50 miles per hour and the robber with his swag is stood on the roof. Got these two cops here, both fire their guns at the robber. The bullets move at 100 miles per hour. Now, the cop on the train, his bullet will strike the robber at 100 miles per hour, okay, because they're both stood on the train. However, the cop stood on this pile of boxes as the train passes by. His bullet will only hit the robber at 50 miles per hour because the train itself is moving at 50 miles per hour. And so the relative speed of this bullet to the train is only 50 miles per hour. So that is so far so intuitive. But what happens if they have laser guns? They're firing light at the robber. Well, light moves at the speed of light, and relativity says that the speed of light is constant in all frames of reference. That means that the light fired by cop A will strike the robber at the speed of light, but so will the light from cop B, despite the fact that the train is moving at 50 miles per hour relative to cop B, but is not moving at all relative to cop A. So that's weird. How does that work? How does the relative motion not affect the observed speed of light? Well, in order to make that work, Einstein realized that the faster that something moves, the slower time appears to move for it. And we have verified this experimentally many times now. For example, for every second that passes on Earth, 0.99999999967 seconds passes on the International Space Station, which is orbiting at about 77,000 miles per hour. So because it's moving relative to us at a highish speed, time is moving slower for it than it is for us, relative to our point of view. Now, obviously, it's not moving much slower, and that's because 77,000 miles per hour is still a tiny speed compared to the speed of light, 180,000 miles per second. Still, it adds up to about 4 seconds of difference per year. GPS satellites have to correct for this, or they will give the wrong position by about 10 kilometers after a single day. So this is called time dilation. Okay, so that is one of the main predictions of special relativity. Let's move to general relativity. Einstein realized that the force of gravity actually feels a lot like just being in an accelerating frame of reference. If something accelerates relative to something else, it's going to feel to them like they're in a gravitational field. Picture yourself in an elevator, for example. As the elevator starts to accelerate up, you initially feel as though gravity has got a little stronger. You feel heavier for a moment until you've got up to a constant velocity, and then you return to normal. So Einstein took this observation and he took it seriously. He said, well, if if gravity and acceleration appear the same, let's just say that they are the same. Gravity is no longer a force like the other forces. It is what happens when you try and move in a straight line, but something causes you to accelerate. And the thing that causes you to accelerate is actually that you are moving in curved space-time. So how does that work? Well, I'll give you the 2D analogy that is usually given, but you should take this with a little, well, it works a little like this. Here's the sun, and suppose you treat space-time as a rubber sheet and you place the sun on that rubber sheet. What Einstein says is the mass of the sun will deform that rubber sheet. So it's kind of analogous to you putting a heavy bowling ball on that rubber sheet. Now, if you stretch that rubber sheet out, before you place the sun there, the sheet is flat, and if you rolled a marble across it, it would move in a straight line. But if it is curved because of a mass there, because the sun is there, and you rolled a marble across it, and let's call the marble Earth, then that marble is going to follow a curved trajectory. And if you roll it just right, it'll start rolling around the center here, the sun, in roughly a circle, just like the Earth moves around the sun in a circle. Now that's not because the sun is attracting the Earth in this picture. It's because the Earth is just trying to move in a straight line, but space itself is curved. So the best straight line that the Earth can follow takes it around the sun like this. There's another effect. For two objects, the one in the stronger gravitational field will see time running slower for the object in the weaker gravitational. This is gravitational time dilation and is a separate effect from the time dilation we saw in special relativity. Once again, we are in a stronger gravitational field than GPS satellites, which means that the clocks on those satellites will appear to run slower. If this is not taken into account, we're going to end up with errors of 10 kilometers per day. So the fact that you can find yourself on a map on your mobile phone, so the fact that your cell phone can tell you exactly where you are to within a few meters proves that general relativity is correct and that space really is curved. So as I said, this is gravitational time dilation. Another effect is that light moving outwards in a gravitational field will lose energy, and lower energy light is redder. Light falling in gains energy and therefore becomes bluer. This is gravitational red or blue shift. And the final effect I'm going to cover is that if object is rotating, it will actually drag space-time around with it like a whirlpool. Remarkably enough, we've detected this effect for the Earth. The Earth, in the scheme of things, isn't very massive. It is dragging space-time around it to a tiny extent, enough that we've been able to measure it. Okay, now let's talk a little bit about escape velocity. Now you're going to do some estimates like this as a homework. Let's ask, how fast do you have to throw a ball up for it to escape the Earth completely? Well, you can figure that out by just setting the kinetic energy equal to the gravitational potential energy of an object. Right? If you throw it up with an initial kinetic energy that is equal to its gravitational potential energy, then it will just about escape the gravitational pull of the object you're on. So that depends on the mass of the object and your distance from the center of the object. So if you're on the surface of the Earth, the escape velocity is around 25,000 miles per hour. That's 11 kilometers per second. And it doesn't actually decrease that much if you go into orbit. If you built a 1,000-mile high tower and threw the ball up from there, you'd still have to throw it at about 22,000 miles per hour, or 10 kilometers per second. If you're at the surface of the sun, the mass is bigger and the radius is bigger as well. The escape velocity then is about close to 1.5 million miles per hour, or about 600 kilometers per second. A white dwarf has the mass of the sun but the radius of the Earth. From the surface of a white dwarf, the escape velocity is about 14.5 million miles per hour, or 6,500 kilometers per second. And from the surface of a neutron star, we already established it's about half the speed of light, or about 165,000 kilometers per second. So let's put these up there. In 1783, the Reverend John Mitchell noticed a strange consequence of Newton's laws of motion and gravity. An object with the same density as the Sun, but 500 times its radius, would actually have an escape velocity greater than the speed of light. You can see it in these numbers here. If we keep making things denser and denser, then eventually the escape velocity is going to go above 300,000 kilometers per second. And so even light is not going to be able to escape the object. A neutron star comes close. It's about 10 kilometers across. For the escape velocity to exceed the speed of light, you'd need to collapse it down to 3 kilometers. If an object has an escape velocity greater than that speed, then light cannot even escape its surface, and from the outside it would appear black. We would never see anything come from that object, and we would have a black hole. Now, the radius that you have to squash something down to in order for the speed of light to exceed the escape velocity is known as the Schwarzschild radius. For the Sun, it's around 3 kilometers. For the Earth, you'd have to squash the Earth down into about 1/3 of an inch in order to get a black hole. For a human, we'd have to get squashed down to about 10 to the minus 23 meters in size in order for us to become a black hole. That's about 10 million times smaller than a proton. So we have our answer. What happens at the end of lives of the most massive stars? It collapses inwards until all of its matter has fallen beyond the Schwarzschild radius of 3 kilometers. It is then a black hole. We call black holes that form this way stellar mass black holes because they have masses close to the mass of the core of the star that produced it. And they tend to be around 3 to 10 times the mass of the Sun. Any event that takes place inside the Schwarzschild radius of a black hole can never be seen by the outside universe. So the Schwarzschild radius is effectively the boundary of the black hole, its surface. It has no solid surface, so this is essentially what we've decided as the best definition. And it is known as the event horizon. So on Earth, the horizon is just that point beyond which you can't see anything, and the same is true for a black hole. All details of the matter that have fallen into the black hole are destroyed. The only information about the matter that fell in that persists is its mass, its angular momentum, and its electric charge. In most astrophysical situations, the matter that falls in is neutral, is electrically neutral. So any black hole that we see is characterized only by its mass and its angular momentum. There is no internal structure, no solid surface, no features. It is just something with a mass and a spin. Now, one misconception that people have about black holes is, for example, if the Sun turned into a black hole today, people will assume we're all going to be sucked in. That is not the case. Far from the black hole, if you're at distances significantly greater than the Schwarzschild radius away from the black hole, the gravity appears to be normal. It appears to be the same gravity as the object that collapsed to form the black. So if the Sun were to suddenly collapse into a black hole, the orbits of the planets would be unaffected. We would just keep on orbiting in exactly the same orbit. The only difference is we would no longer get any light and energy from the Sun, which admittedly would be a rather radical change, but gravitationally everything would still be the same. It is only very close to a black hole that gravity becomes extremely strong. If you get closer than about 3 times the Schwarzschild radius, you would be unable to escape. In a general relativity picture, an ordinary star curves space to some extent. A neutron star, something more dense but the same mass as an ordinary star, would curve it even more. For a black hole, space-time at the center has become infinitely curved, and that point of infinite curvature is known as the singularity. Classically, all matter that collapses to form a black hole will disappear into the singularity and disappear altogether to a point of infinite density. Now, in real life, we expect that doesn't quite happen. When the matter gets squashed down to microscopic proportions, we expect the laws of quantum physics to come into play and something else to happen. But we have no good theory yet of how quantum physics combines with general relativity, so we don't know for certain what happens at the very center of a black hole. That is still an active area of research. So here's the basic picture of a black hole: a singularity and an event horizon out at the Schwarzschild radius, which is about 2 times Newton's gravitational constant times the mass of whatever it is that fell in to form the black hole, divided by the speed of light squared. If you jump into a black hole, what would happen, according to an observer far away from the black hole, is that you would start off normal, and as you move in, your gravity would start to stretch you. It would stretch you more and more. You would become redder and redder. Okay, light coming from you would be redshifted more and more as it got back to an observer far away. And also, it would appear that you were slowing down. Time would appear to get slower for you, according to an observer who is sat safely far away over here. Finally, how do we see black holes? Well, we don't directly because they're black, but we see their effects on nearby gas and stars. Particularly, stars orbiting black holes appear to wobble when we observe them. We see X-rays from disks of gas falling into a black hole. Here's an artist's impression of an ordinary star whose outer layers are being drawn into a so-called accretion disk, and they move inwards kind of like a whirlpool of matter. Friction heats the material up to millions of degrees Kelvin, hot enough to emit X-rays from the very central regions of the accretion disk. And those X-rays we can see. Here is an example of an image of a particular system, Cygnus X1, which is an X-ray image presented in false color. The other way of seeing them is their gravitational effects on their surrounding. So if you have a star with a black hole companion, then you won't see the black hole, but this star will appear to wobble. What it's actually doing is orbiting something that is unseen. Next week, we'll see what the effect of the black hole at the center of the Milky Way galaxy has on the stars close to the center of the galaxy.